Welcome to the homework solutions video for assignment 3.08 number 2. So these are questions 7, 8, and 9 from pages 544 and 545 of the textbook. So we are going to use Desmos to get them solved here. So in question 7, we are given a table with months and average temperatures. So Sally is trying to make predictions before her trip to Yellowknife next June. So let's start by entering that data. All right, so now the magic of pausing a recording has allowed us to get all of the data points in here. We need to make sure we can actually see them. So we're going to make it a little more clear for the recording by putting it into our projector mode. Now we know our domain. So the month numbers run from 1 to 24, so I'm going to make our domain 0 to 25. That'll allow us to have everything in and out of that range. The lowest temperature we see is negative 25.6. So I'm going to pick a negative 30 for the low end of the Y. The highest temperature that we see appears to be 17.9, so I'm going to go to 20. So here is our data. Now we want to find the equation of a sinusoidal regression function that models the average temperatures. So use y1. The tilde means we are regressing the data. A sine b x1 minus c plus d. Now that we have all the variables, Desmos has regressed the data, and we found that these are our points. So our A is 20.3418. That's our amplitude. Means you have about a 40-degree range. Our B, that's our period, 0.536. That's roughly 2 pi. So 2 pi over B is roughly 12, which is what we'd be looking for. Our C function is the phase shift. That's how many months in we are before we get the upswing. It's a little over 4. And then D is negative 2.7, so this is the average temperature. So question part B asks us to determine the maximum and minimum values. So our maximum will be the amplitude plus the D. So that's about 17.6 degrees is the warmest we can really expect Yellowknife to be if these are typical years. The minimum is a negative 23.051. That's the coldest we can expect Yellowknife to be in these typical years. And asking, what do these values show about the accuracy of the regression function? Well, the fact that our max is 17.6 when we actually have a point at 17.9 tells us that it's a little bit off. Same with a low point, that negative 25.6 is a little below the regression. So the extremes were actually more extreme. So it might take a few more data points before we can do this. Or there might be something else going on. We might be seeing the effects of climate change changing our averages over these years. So it's fair, but it's not perfect. So then finally, based on your sinusoidal regression function, what will be the average temperature in June of next year? So June of next year would be month 30. So we're expecting the average temperature to be about 16 degrees. Okay, so that concludes question 8. Question 7, that was question 7, this is question 8. It's a table with hours of daylight in Regina, which is at a latitude of 50 degrees. And we have day of the year and the hours of daylight. So I will again pause while we enter that data. All right, our data has been entered, but again, we need to make sure we are looking at it. So the day of the year runs from 15 to 349, so we'll go from, say, 0 to 364. And our range, the lowest value I'm seeing on the table is 8.1, so let's go with, say, 7.5. The highest I see is 17.1, so let's go with, say, 20. And now we have a model for the amount of hours of daylight in Regina for this 12-year period. So we are again going to do a regression model. Okay, so this is our model. We have our A, B, C, and D values. Determine the range between the maximum and minimum hours of daylight in Regina rounded to the nearest minute. So 16.619 minus 8.205. So if we just subtract these, it's 8.414. So if we take our 0.414 and multiply it by 60, because that's the fraction of the hour, rounded to the nearest minute, that is about 25 minutes. So it works out to 24.84 if we take 0.414 and multiply by 60. So there's roughly 8 hours and 25 minutes. So which day has the most hours of daylight? That appears to be day 171. So which day is that on the calendar? If we take 171, there's 31 days in January, so that leaves us with 140 days. We'll assume this is not a leap year, subtract 28 days for February, subtract 31 days for March, subtract 30 days for April, subtract 31 days for May, and we're at 20. So this works out to June 20th, which is exactly what we would expect. And the hours of daylight in Regina on day 30, rounded to the nearest minute. So day 30 gives us 9.173. So 0.173 times 60 is 10.38. So we're looking at about 9 hours and 10 minutes of daylight on day 30. And then finally determine which days of the year have about 15 hours of daylight. So that would be, looks like day 119 and day 224. So day 119, we go 31 plus 28. So the last day of February is day 59. Last day of March is day 90. And then day 120 is April 30th. So day 119 must be April 29th. Add another 31. We're 151 days in for the end of May. 30 days for June takes us to 181. 31 days for July takes us to 212. So August 12th is the other day. So that wraps up question 8. So now for question 9, I'm going to try just adding the table as it is. So let's just try replacing these with ones. Question 9 is the average monthly temperature and precipitation in Edmonton. So we have to find the temperatures and the precipitation. So we actually have 2 charts to fix here, or to do. So the first one is just months of the year. We'll need 12 of those. And then our temperature is negative 13.9, negative 5.4, 6, 14.7, 17.4. We see we're getting some data here. So let's make our x-axis cover just that year. Looking at our data, there's our y-axis. So as we enter more data, we enter in the 17.3 for August. Each data point we enter, we can see the curve shifting a little bit as the new data comes in and is taken into account in the regression. So here is our full year regression. So we want to find the average temperature in January or in next January to the nearest tenth of a degree. So when we have x equal to 13, we're looking at, on average, negative 12.9. And now we want to find the average precipitation in January. So that is going to be a very different curve, because our precipitation data ranges from 0 to 88. I'm going to put it in as 100 as the upper limit. So we have a 22, a 9, and as we enter this new data, we'll see each data point pulling that regression curve up, since we've got half of one curve and half of another. So there we go. That has bent and twisted it to where we are at. I'm just checking the outliers. So here we want to find the prediction to the nearest millimeter. For the precipitation in January, that's 36. We want to ask which is more reliable. To me, it looks like the temperature data is more reliable, because this precipitation data is not as good a fit. The data points on average are much further from the graph. So I do not believe that the precipitation is as reliable as that temperature was. That concludes the homework solutions for 3.05, number 2.